Welcome to NPTEL online course on fractal and multifractal. In the last lecture, we have discussed the how to find the fractal dimension using the box counting theorem. So, in which we have obtained the fractal dimension for smooth object in the Euclidean space by covering them by boxes of some sizes of by using the 1 by 2 power n side lengths, we have obtained the fractal dimensions. Whereas not yet we covered the how to obtain the fractal dimension for the real fractal object, because the fractal dimension we can calculate for any set. Now we are going to calculate the our fractal set which we discussed in our previous classes, the classical fractal sets, Cantor set, Van Koch curve and the Sierpinski triangle. For these sets we are going to obtain the fractal dimension by using the box counting theorem. Let us recall what is the box counting theorem. Let A belongs to h of r power m, where r power m is the m tuple ordered tuple of real numbers, set of all m ordered tuple of real numbers. Then h of r power n is set of all non-empty compact subsets of r power m, where the Euclidean metric is used to say r power m is matrix and h of m comma r power m with the Hausdorff metric is metric space. We are using the Euclidean matrix. We can cover r power m by closed square boxes of side length 1 by 2 power n. Then n of A denote the number of boxes of side length 1 by 2 power n which intersect the attractor desired set which we want to find the fractal dimension. If d equal to limit n tends to infinity, ln of n of A over ln of 2 power n, then d is called the box counting dimension of A or fractal dimension of A. In the last class, we obtained that the box counting dimension of the line segment is equal to 1, which is we obtained as which is equal to 1. And if you are taking any singleton set in general in r power n, the box counting dimension of this is equal to 1. Not only in r power n, in general metric space, if you are taking any finite set, the box counting dimension of the singleton set is 0, not 1. If you are taking any finite set, the box counting dimension of the finite set is 0, which we proved in the last lecture. Now let us discuss the box counting dimension or fractal dimension of Van Koch curve. Now use the box counting theorem to calculate the fractal dimension of Van Koch curve K. So consider the Van Koch curve K is subset of r power 2. Now we are taking r power 2, that means we are taking m equal to 2, and our Van Koch curve may be this one, not this one. Van Koch curve, this notation belongs to r power 2, that is equal to k. At step n, the Van Koch curve consisting of 4 power n line segments, each of its length is 1 by 2 power n. I just recall how we constructed the Van Koch curve. We need to take the line segment 0 and 1, dividing this as 3 equal parts. Then now we need to remove this mid part. Then after removing, instead of giving the gap here, we have to make that as a side of an equilateral triangle. This is 1 by 3, this is 2 by 3. Now we will make as the side of an equilateral triangle. Maybe I will work here. This is 2 by 3, this is 1. Now we have 1, 2, 3, 4 line segment. After first iteration, we have 4 line segments. Each of its length is 1 by 3. Now you can do the same same procedure on the first iteration, one can get this type of in the first line segment. In the second line segment, one can get this type of line segment. One can get this type of curve, and similarly here one can get this type of curve, and here it is goes to here it is goes to again this one, and like this one and this one and this one. So, this is 0 and 1, this is 1 by 3, this is 2 by 3, this is we will get 1 by 9, 1 by 9, 2 by 9, this is 8 by 9, this is 7 by 9. Like that we will get the points. So, here you can consider this part. In this part we have 1, 2, 3, 4 line segment, each of its length is 1 by 9. So, here 4 line segment of length 1 by 9, here also same 4 line segment of length 1 by 9, similarly here and similarly here. So, end of the second iteration we have 4 power 2, 4, 4, 8 plus 12 plus 16, 4 power 2 number of line segment, each of its length is 1 by 3 square. You can continue this process. So, after the nth step one can get 4 power n number of line segment, each of its length is 1 by 3 power n. Now, after the n tends to infinity, one can get the von Koch curve. So, therefore, in each iteration von Koch curve consisting of 4 power n line segment. Therefore, in each for covering this line segment, after the first iteration, if you want to cover the line segment, you can use this box and this box and this box. We need 4 boxes of length 1 by 3, side length 1 by 3. Therefore, now cover r power 2 using the boxes of side length epsilon equal to 1 by 3 power n, that means epsilon equal to 1 by 3 power n. Now, you are covering r power 2 using 1 by 3 power n. Fine. Now, the number of boxes, each segment of length 1 by 3 power n can be covered by a finite number of sub boxes, because every infinite cover has the finite sub cover, can be covered with a finite number of sub boxes. Hence, the number of boxes intersecting k, because we need to find the k is an attractor von Koch curve. So, it is satisfying the number of boxes required to cover k, the minimum number of boxes required to cover k is 4 power n, 4 power n. Now, the number of, as per the box counting theorem, the limit n tends to infinity, ln n of k over ln 1 by epsilon equal to, here it is 4 power n, this is 3 power n, then one can get limit n tends to infinity n times ln 4 over n times ln 3. So, this n will cancel, this does not depends on n, then ln 4 by ln 3. Therefore, the box counting dimension of the von Koch curve k is ln 4 by ln 3. This result is sketched here, one can observe. This is the box counting definition. This is the first step, the Koch curve construction. The first step, in the 0 step, we have the initial line segment 0, 1. Then here we are dividing 3 equal part, removing the mid part, then making it as a side of an equilateral triangle. Now, we have the 4 line segment, 1, 2, 3, 4 line segment, each of its length is 1 by 3, because we are dividing this 3 equal parts and removing the mid one and making at the side of an equilateral triangle. Therefore, both the side length is same, it is equal to 1 by 3. In the second step, one can get this one 4 power 2 triangle, this is after the third step, after the nth step one can get 4 power n segments of side length 1 by 3 power n. So, this is the Van Koch curve construction. Now, you can observe in the first step, we can take n naught, that means n equal to 0, epsilon equal to 1 by 3 power 0 equal to 1, that means epsilon of radius 1. Then you can take the single line segment is enough to cover this one, because it is in r power 2, side length 1 we are covering this one by a straight line. Now, if n equal to 1, we have the 4 line segments, then epsilon equal to 1 by 3 power 1 equal to 1 by 3. So, we need the 1, 2, 3, 4 boxes of side length 1 by 3 is needed to cover here, and if n is 2, then we need 4 power 2, 16 number of boxes of side length 1 by 9 is required to cover this object, and so on. Now, you can plot the ln of 1 by epsilon, and the ln of n of epsilon. One can get this one with respect to the iteration ln 4 by ln 3. Here it is ln 4, this is 2 ln 3. So, here it is, you can get 2 ln 3, 3 ln 3, 16s here and 64 here and 4 and here. Ln 2 is repeating here, maybe this is not works. This will come to here, and 4 means this will come to ln 4 by this here, and 64 for 3. Just ignore this one. Only ln 16 you can write ln 4 power 2 by ln 3 power 2. So, 3 power 2. So, you can 2 will cancel, ln 4 by ln 2, ln 3 after second iteration. So, the slope of this curve is ln 4 by ln 2. This is the box counting dimension of Van Koch curve. One can observe that the box counting dimension of ln 4 by ln 3, that means the box counting dimension of the Van Koch curve is ln 4 by ln 3, which is approximately equal to 1.2619. Now, this Van Koch curve K is embedded in r power 2, and this dimension is 1.2, whereas the dimension of r power 2, box counting dimension of r power 2, that box counting dimension of r power 2 is 2, and the box counting dimension of Koch curve is 1.2619, which is strictly less than the embedded space dimension. You can note down this one. Therefore, we can call the box counting dimension, the Van Koch curve is an example for a fractal. Now, let us try to find one more classical fractal dimension. Now, let us try to find the fractal dimension of one more classical set Sierpinski triangle. Use the box counting theorem, same box counting theorem, to calculate the fractal dimension of Sierpinski triangle with the box side length 1 by 2 power n. Now, consider the classical Sierpinski triangle S in r power 2. At each step n, the Sierpinski triangle consisting of 3 power n triangle of side length 1 by 2 power n. How it is? Now, in the Sierpinski gasket or triangle, we started with the triangle of side length 1. We are dividing it to each side as 1 by 2 equal lengths. Then after this state, what we did, instead of removing it, we are joining the midpoints and connecting the midpoints like this one, and remove the interior, not the, just to remove the interior here like this one. This is the first step. In the next step, now if the side length are 1, here we have one triangle of length 1 here. here we have 1, 2, 3 triangle of length 1 by 2. Side length is, the length means the side length is 1 by 2. Now applying the same process here, then one can get, now we need to divide this and 1 by 2 of length like this one. Then we need to connect the midpoints. Then one can get this type of triangle. So I am drawing here. This is the given equilateral triangle. All the side length is 1. Then after the first iteration we are getting this triangle. So the second iteration we are getting this triangle second, and here like we are getting like this one. Now you can observe here we have 3 triangle of length 1 by 2. Now here 3 triangle of length 1 by 4, because this the side length is up to here it is 1. The side length is 1, therefore here 1 by 4, 1 by 4, 1 by 4 and 1 by 4. Therefore each subtriangle side length is 1 by 4. Here 3 triangle, here 3 triangle, here 3 triangle. Totally 9 triangles of length 1 by 4, which means 1 by 2 power length side length of the triangle. Totally we have 3 power 2 triangle. So likewise, if you are continuing this process, after nth step we have 3 power n triangle, each of which side length is 1 by 2 power n. Now because this Sierpinski gasket is contained in r power 2. Now cover the r power 2 by the box of side length 1 by 2 power n. Box of side length 1 by 2 power n. Then each small triangle of side length 1 by 2 power n can be covered by a finite number of such boxes. Hence the number of boxes intersecting the S, the Sierpinski triangle S, is 3 power n. Now use the box counting technique. Limit n tends to infinity, ln n of s by ln 1 by s. Again by the same technique we used in the von Koch curve, one can get n will come to here and ln 3 by ln 2. So again there is no involvement of n, ln 3 by ln 2. In each iteration we are getting the box counting dimension or fractal dimension of a Sierpinski triangle as ln 3 by ln 2. Now this is the box counting dimension of a Sierpinski triangle ln 3 by ln 2. Now it process is explained here. Here we are taking the equilateral triangle with the interior. So now we need to divide this. Maybe I will take some this color, and now I dividing this as 3 equal parts. Sorry, not a 3 equal parts. I am dividing the side length as 1 by 2. Now connecting the midpoints like this one and remove the interior, not an boundary. Boundary is included, so that after the first step, after the first iteration, one can get this type of triangle. The same process here, divide as 2 equal parts. Now connect the midpoints like this one, then remove the interior, one can get this object. That continue this process. After the nth iteration, one can get the Sierpinski triangle like this one. Now you can take any part of this object, it reflect the whole. Obviously it is satisfying the self similar property which we already discussed. Now you can observe here we have only one triangle. We started with the one triangle. So after the first iteration we get 3 triangle of length 1 by 2, side length 1 by 2. Here 3 power 2 triangle of side length 1 by 2 power 2, and so on, like it would get. So after the nth iteration we will get 3 power n triangle of side length 1 by 2 power n. Now this Sierpinski triangle is embedded in r power 2. Now you can see, if you are taking n equal to 0 and epsilon equal to 1, then we need only one box of side length 1 which covers the box, the triangle. Now you can take n equal to 1 and epsilon equal to 1 by 2. We need 3 boxes is required intersect the Sierpinski triangle. Now finally, maybe here you can come, this is in r power 2, and the r power 2 you can cover r power 2 by epsilon equal to 1 by 2 power n triangle. Then each triangle will intersect. There are 3 power n triangle, 3 power n triangle of side length 1 by 2 power n definitely intersect this Sierpinski triangle, because we are covering r power n by 1 by 2 power n boxes, in which 3 power n number of boxes of side length 1 by 2 power n will intersect the attractor, that means our Sierpinski triangle. Therefore, this is the number of box required to cover the set, and this is the size of the boxes. Therefore, we can apply this theorem, box counting theorem. The number of boxes is ln 3 power n over ln 2 power n. One can get 1.5 as the box counting dimension of the Sierpinski triangle. And the same way, like the von Koch plot the ln 1 by epsilon over ln of number of boxes, find the slope, one can get the box counting dimension in alternative way. Now you can observe that the Sierpinski triangle is embedded in r power 2, then the box counting dimension of r power 2, as we discussed, it is 2. Whereas the Sierpinski triangles, the box counting dimension is 1.5850 approximately, the approximation of ln 3 by ln 2. Then the dimension of the Sierpinski triangle is less than the dimension of its embedded space. So it is a fractal object, it satisfying the fractal definition with respect to the dimension property. Also, if you take any subpart of this triangle, it will reflect the whole, it resembles the whole, it will satisfy both the property, similar like the von Koch curve. Now let us find the fractal dimension of a Cantor set by using the same box counting theorem. Consider the classical Cantor set C. Previously, Koch curve as well as the Sierpinski triangle, both are embedded in r power 2. Both are embedded in r power 2, whereas Cantor set is embedded in r. We know that the box counting dimension of the r is 1. Now we need to find what is the box counting dimension of Cantor set. At each step, nth stage in the construction of Cantor set, it has 2 power n disjoint closed interval, each has the length 1 by 3 power n. How? I just quickly explain. 0 to 1, we are dividing 3 equal part and removing this mid open interval, and so on you need to go. Then this one is the after the first iteration. If you remove second iteration like this one can get, and so on it will go. So after the nth iteration, here we have one interval of length 1, here we have 2 interval of length 1 by 3, here we have the 4 interval of length 1 by 3 power 2. Therefore, after the nth step, one can get 2 power n interval of length 1 by 3 power n, that we mentioned here. Now cover the R using the boxes of side length 1 by 3 power n, 1 by 3 power n. Each interval of length 1 by 3 power n can be covered by the exactly 1 boxes. Hence the number of boxes intersecting C is 2 power n. For example, this is our real line. Consider this as our real line, minus infinity to plus infinity. Take n equal to 1. That means after the first stage, this is 0, this is 1 by 3, this is 2 by 3 and this is 1. If you are taking n equal to 1, we are covering throughout this real number system by using the epsilon as 1 by 3. So, what is our box? X minus 1 by 3 comma x plus 1 by 3. This is our closed balls is required to cover the real number. We can take union of collection of all such boxes x belongs to R, which covers the real number. You noted that if you are taking any number in between here 0 and 1, it will covers the closed interval 0 comma 1 by 3. If you are taking here and 1 by 3, it will not cover, it will goes here. If you are taking the midpoint, it will exactly cover this two number. If you are taking midpoint, it will exactly cover here. So, there are two boxes because it may get 4 boxes also cover with the same side length, that means same interval length, whereas we need to take minimum among all the covers, minimum among all our. So, if you are taking the midpoint, then there are 2 boxes exactly is needed to cover this set 0 comma 1 by 3 and 2 by 3 comma 1. Therefore, only 2 boxes are needed. Therefore, you can write here n of C1. Why I am writing? After the first stage, n of number of boxes is required to cover the C1 is 2 and epsilon equal to 1 by 3. Then you can apply the box counting dimension, you will theorem, you can get ln 2 by ln 3. So, now this is in the C1th state. If we are going the infinite number of iteration, nth iteration, we need the box sizes of length 1 by 3 power n, that means a box of side length 1 by 3 power n. So, each interval of length 1 by 3 power n can be covered by exactly one such a box it will cover after the nth iteration. Hence, the number of boxes is intersecting C is 1 by 3 power n length boxes cover exactly one such a boxes. We have 2 power n number of boxes in each iteration, therefore 2 power n number of boxes is needed to cover. If you are applying the box counting theorem, one can get ln of n of C by ln of 1 by epsilon, then one can get this ln 2 by ln 3. It is explained. So, the box counting dimension of the Cantor set is ln 2 by ln 3. Now, this is explained here. This is the mid end of Cantor set. If you are taking the closed interval 0 comma 1, this is epsilon as 1, then we need the only one box. If you are taking here, it is the 2 state. If you are taking epsilon as 1 by 3, that means n as 1, epsilon as 1 by 3, there are 2 boxes. These 2 boxes is needed to cover these 2 sets. And similarly, if n equal to 2, that means 1 by 9 side length, that means the interval length, we need 4 boxes. Here it is 1, 2, here one, not here, here there are 2 boxes is needed to cover the Cantor set in the second iteration. Likewise, it continues on. If you are plotting the number of boxes versus its lengths, then you can find the slope, one can get the box counting dimension. So, we can conclude that the box counting dimension of the Cantor set is ln 2 by ln 3. The box counting dimension of the Cantor set is ln 2 by ln 3, which is equal to 0.6309. So, C is embedded in more precisely closed interval 0 comma 1. In the previous class, we have discussed this. The Cantor set dimension is 0.6309. The box counting dimension of 0 comma 1 with respect to the Manhattan metric as well as with respect to the Euclidean matrix, it is equal to 1, which is this number is strictly less than the dimension of the embedded space 0 comma 1, more precisely, which is equal to 1, more precisely the real number systems. Now, the Cantor set here exhibit the self similar nature. At each step you can take, it will matches the whole, and the comparing the box counting dimension of the Cantor set at an embedded space. This is 0.6 and 1, it is less than the embedded space box counting dimension. Therefore, the Cantor set also in a fractal object. So, likewise we can find the fractal dimension of any object in R power n by using the covering of the object, that means the covering of the whole space. If you are taking object from R, cover the R by boxes of side lengths 1 by 2 power n, and according to the set's nature we can cover, then find the number of boxes intersect that attractor, that means the set, then take the logarithmic of minimum number of boxes required to cover intersect the attractor over its box sizes, then one can get the box counting dimension of the attractor. So, thank you, and the reference one can refer these books for more further reference. Thank you.